Let us begin with an overview of today's lesson, Dimensionality Reduction using PCA, or Principal Component Analysis. We will see how PCA helps simplify data by reducing its feature count and still keeps the most important information. You will learn how to use PCA in Python step by step. Week 3, Dimensionality Reduction with PCA. Welcome! Today, we will learn how PCA, Principal Component Analysis, simplifies complex data, why it is useful, and how to use it with real datasets in Python. By the end, you will know how to reduce unnecessary features and create clearer data visuals. Running the cell now. Think of PCA as helping you find the most helpful directions in your data. What would you like to predict or understand with fewer features? Let us set up our notebook to ignore warning messages. This keeps our output simple and helps us focus on learning the essentials. This line is just a comment to remind us we are turning off warnings. We import the warnings library. Import numpy as np. We set the random seed to 42 for reproducibility. We tell Python to ignore warning messages when they show up. Running the cell now. Here, we prepared our environment by setting a random seed for reproducibility and suppressing warnings to keep the output clean and focused. While this step doesn't produce visible results, it ensures that the PCA workflow runs smoothly and consistently as we explore dimensionality reduction in this lesson. Now we are ready to explore data without distractions from warnings. Let us talk about what dimensionality reduction means in simple words. What is dimensionality reduction? Machine learning data can have many features. Dimensionality reduction means lowering the number of these features while keeping the key information. Why do we do it? Too many features can make models slow, confusing, or hard to visualize. Imagine shopping online and having hundreds of filters. PCA helps us find which filters matter most. Running the cell now. Think about other times too much information makes things confusing. Where might you want only the most important parts? Let us load our sample dataset for today. We will use the famous iris flower dataset. This comment describes what the cell does, loading data. We import the pandas library so we can handle data easily. We give pandas the web address where our data lives. We use pandas to download and read the data from the web, storing it as a new table called df. We print out the shape to see how many rows and columns there are. We show the first 3 rows to get a quick peek at what the data looks like. Running the cell now. The output shows that our iris dataset has 150 rows and 5 columns, including 4 numeric features and 1 species label. The sample rows reveal consistent feature measurements like sepal and petal dimensions, which are the key data we'll later reduce in dimensionality to simplify analysis while preserving important information. This initial exploration helps us understand our starting point before applying dimensionality reduction techniques. Try looking closely at the table. There are 4 features for each flower plus the species name. Can you read and understand what each column means? Now, let us see what PCA really is. What is PCA? PCA stands for Principal Component Analysis. It finds the directions that capture the most information in our data. We use PCA to make big datasets simpler and to help visualize data in 2 or 3 dimensions. Running the cell now. Think of PCA as finding the most revealing angle from which to look at your data. Let us inspect our data. We will see each column's type and if there are any missing values. This is a note that we are doing data inspection. We print out the types of each column, such as number or text. We check how many missing values there are for each column. Running the cell now. This output shows the data types and missing values in our dataset, confirming all feature columns are numeric floats and there are no missing values. This is important for PCA, as it requires numerical input without gaps to effectively find the directions capturing the most variance. Noticing that species is an object type reminds us it's a categorical label, used later for interpretation rather than the PCA calculation itself. Well done! Knowing your data types is the first step in any real project. Are you surprised by the data types or missing values? To use PCA, we only need the number features, not the text labels. This reminds us that PCA works with numbers, not labels. We remove the species column and keep only the numeric parts. We preview the numeric feature table using .head. Running the cell now. Here, we've isolated the numeric features from the Iris dataset by removing the species column, which PCA won't use since it's categorical. Notice the dataset shape is unchanged but now only includes measurements like sepal and petal lengths and widths. These numeric values are what PCA will analyze to find the patterns that explain the most variance in the data. Notice that we have just the measurements here, not the species. Why do you think labels are not needed for PCA? Let us make sure all measurements are on the same scale. This is called normalizing, and it is important for good PCA results. We note that PCA needs features to be balanced, or similar in size. We import the standard scalar tool from scikit-learn. We create a scalar object to handle our data scaling. We scale all numeric feature columns so each has mean 0 and unit variance. We print out the first 3 scaled rows for a quick check. Running the cell now. Here, we see the first 3 rows of our feature matrix after normalization, where each column now has a mean of 0 and a standard deviation of 1. This scaling is crucial because PCA is sensitive to the ranges of features and performs best when all inputs are on a comparable scale. Notice how the values cluster around 0, preparing the data for accurate principal component extraction. See how the values have changed? Scaling helps prevent large numbers from dominating PCA. Can you imagine why scaling is needed? Here is a simple way to picture what PCA is doing underneath. How does PCA work? PCA rotates your data to new directions, called principal components. The first direction explains as much of your data as possible. The second direction explains the next largest amount, and so on. Think of it like finding the best angle to look at a busy street so you can see the most action. Running the cell now. Try sketching a scatter plot and imagine rotating it. Which direction would you turn it for the widest view? Now we will use PCA to shrink our 4 measurement columns down to just 2 important axes. This helps for plotting. We mentioned that we will shrink the data to 2 parts. We import the PCA tool from scikit-learn. We tell PCA to figure out the 2 best directions, or components. We fit our PCA to the scaled data and transform it to get the new view. We show the new shape to see it only has 2 columns now. We print out the first 3 rows to see the new numbers. Running the cell now. After applying PCA to the scaled Iris data, the output shape, 152, shows we've reduced the original features to 2 principal components, capturing the most important variance. The first few rows display transformed data points in this new rotated coordinate system, illustrating how PCA compresses information into fewer dimensions for easier visualization and analysis. Nice work! These 2 columns now capture the most important structure in our data. What do you notice about the new numbers? Let us put the species names back with the new principal components, so plotting is easy. We comment that we want labels for visualization. We import NumPy, a handy math library. This helps with data handling. We create a new table from our PCA values and label the columns PC1 and PC2 for principal component 1 and 2. We add the original species labels into our new PCA table for easy grouping. We print out a preview of the merged data set. Running the cell now. This output shows the first 2 principal components, PC1 and PC2, for 3 iris samples, along with their species labels. Notice how PCA has transformed the original features into new axes that capture most variance, while the species column helps us later visualize how different species separate in this new PCA space. This sets the stage for understanding how PCA highlights key patterns across groups. Do you see how each row now has its new PCA features and its species? This makes it easy to color our points later. Let us make a simple plot to see how well PCA separates the different species. We comment that our goal is to visualize separation between groups. We import the plot library, matplotlib. For each unique species, we plot its points using one color. We use the first PCA axis as the x-coordinate and the second as y for all points of the species. We label the x-axis for clarity. We label the y-axis too. We show the species names as a legend. We give our plot a simple title for understanding. Finally, we display the plot we have built. Running the cell now. This scatter plot shows the iris dataset projected onto the first 2 principal components, PC1 and PC2. Notice how the species tend to cluster separately, indicating that these components capture the main variation that distinguishes species. This confirms that PCA effectively rotates the data to new directions that reveal underlying patterns. What patterns do you see? Do the species group together in this new space? Try changing the number of PCA components and see what happens to the plot. You might wonder, how many principal components should we keep? How many components should I keep? PCA lets you pick how many new features, components, to keep. Usually, we keep as many as needed to explain most of the data, often 90% or 95% of the variance. Running the cell now. Remember, fewer components usually mean simpler, but not always better. Let us check how much of the data each new principal component explains. Just a note that we are going to check how much information is captured. We fit PCA to all possible components using our scaled numbers. We grab the share of variance each PCA piece explains. We print the variance for all principal components, so we see what each adds. We sum the first 2 to see how much of the original data they explain together. Running the cell now. The output shows the proportion of variance each principal component captures in the data, with the first component explaining about 73% and the second about 23%. Together, the first 2 components explain roughly 96% of the total variance, indicating that keeping just these 2 captures most of the important information. This confirms the lesson's goal, selecting enough components to explain a high percentage of variance, often around 90 to 95%. Notice that the first few components usually keep most of the information. Can you think of times when you want to keep more components? Let us use another dataset. The Titanic passenger data has more columns and mixing numbers and text. We are trying PCA on a classic dataset. We store the URL for the Titanic CSV file. We load the Titanic dataset into a pandas frame called Titanic_df. We print the shape to check how big the Titanic table is. We take a look at the first 3 rows, just to get a feel for the data. Running the cell now. This output shows the Titanic dataset loaded with 891 rows and 12 columns, giving us a comprehensive view of passengers' information. Noticing key features like age, fare, and P-class here is important because PCA will later transform and reduce this data while preserving most variance. This step sets up the data context before we decide how many principal components to keep based on explained variance. Observe the column types. Can you spot which are numbers and which are text? Practice, pick 2 columns that look interesting to you. We need to clean the Titanic data to run PCA. Let us keep only the number columns and fill gaps with their mean. This note reminds us that PCA works only on numbers. We get just the columns with data types as numbers. We fill any missing values using the average for each column. It helps avoid errors. We preview the clean data to make sure there are no missing values. Running the cell now. This output shows the first 3 rows of the Titanic dataset after filling missing numeric values with the column means, ensuring no gaps in the data before PCA. Notice it includes key numeric columns like age and fair, now complete and ready for dimensionality reduction. This pre-processing step is essential to accurately capture variance when deciding how many PCA components to keep. You have successfully handled missing values. Filling gaps is common in real-world data. Why might filling with a mean not always be the best idea? Let us turn the Titanic numbers into scaled data and then apply PCA, shrinking to 2 main axes. We note that we are now repeating our PCA process. We scale the Titanic numbers to have 0 mean and unit variance. We ask PCA for the 2 most important directions. We fit and transform our scaled numbers into the PCA space. We check the new table shape to confirm it now has 2 columns. We print out the first 3 rows so we can see the new PCA representation. Running the cell now. The output shows the transformed Titanic dataset after scaling and applying PCA, with a shape of 891:2, meaning we reduced the original features to 2 principal components for all 891 passengers. Notice the printed first 3 rows represent each passenger's coordinates in this new 2D feature space, illustrating how PCA compresses the data while retaining key variance. This confirms that by selecting 2 components, we summarize the dataset into fewer features for simpler analysis or modeling. Great job! You have now reduced many Titanic columns to just 2 summary axes. Try repeating this process later with different datasets. Now you get to decide. Choose a number and try PCA with that many components. This is your turn. Adjust the number of principal components for the Titanic data. We ask you to type a number, a small number between 2 and 4. We set PCA to use however many components you choose. We apply PCA, this time getting more columns, 1 for each component. We print the shape to see how many components you used. Running the cell now. This output shows that by choosing 3 components, the PCA transformed the original dataset into a new feature space with 3 columns, representing the key dimensions capturing most variance. Notice the shape, 891:3, means all 891 samples are retained, but now described with fewer features, helping us simplify the data while preserving its structure. This aligns with the lesson's goal of selecting enough components to efficiently explain the data variance. How does the shape change when you pick a higher number? Feel free to rerun with different values until you are comfortable. For our mini-project, let us visualize the Iris dataset using 3 principal components and make a 3D scatter plot. We describe the goal of a 3D PCA plot. We create a PCA that keeps 3 components. We apply it to our scaled Iris data. We import the 3D plotting tool from Matplotlib. We create a new figure with a good size for a 3D plot. We set up a 3D axis on our figure. We assign a different color to each species to help us see them clearly. We loop through each species in the Iris dataset. We create a mask that selects samples from one species. We plot those points in 3D for this species, using their color and a size of 50. We label the first axis, PC1. We label the second, PC2. We label the third, PC3. We show which points stand for which species. We give our plot a title to remember what we are seeing. We display the colorful 3D plot. Running the cell now. This 3D scatter plot shows the Iris dataset projected onto the first 3 principal components, which capture the most variance in the data. Notice how the species form somewhat distinct clusters, indicating that these 3 components retain important structure for classification. This visualization helps confirm that keeping 3 components provides a meaningful, reduced representation of the original features. Now you can see the group spread out in 3 dimensions. Try rotating the plot in your notebook if possible. Do the classes look separate in 3D? Here are a couple of reminders for using PCA in your own projects. It is best to scale your data before you use PCA. Try different component counts and visualize explained variance, or check the plot. Running the cell now. This lesson emphasizes the importance of scaling data before applying PCA and examining the explained variance to decide how many components to keep. Although no textual output appears here, the key next step is to generate a plot or numerical summary showing cumulative variance explained by each component. This helps identify the smallest number of components that capture, for example, 90 to 95% of the total variance, balancing dimensionality reduction and information retention. Challenge: try running PCA on a dataset from your own interests. Remember to check the data's shape and types first. Let us review what you have learned about PCA today. Recap: key points about PCA. PCA helps us explore high-dimensional data by keeping only what matters. Always scale your features before PCA. Use plots and explain variance to decide how many components to keep. Try PCA on new datasets for practice. Running the cell now. You did great today. Try explaining PCA to a friend or family member in your own words. Thank you for learning with us about PCA and dimensionality reduction. Thank you for joining. If you like this lesson, please subscribe to our channel and let us know your favorite PCA insight in the comments. Practice: try PCA with your favorite dataset. Running the cell now. See you next time for more data mining lessons.